So yeah, as Eddie said, I'm going to be talking about something a little bit different. Interesting what they just asked. I'm not a data scientist. I don't know that much machine learning, and a few of the things in the last two great talks definitely went a bit over my head. I'm going to apologize in advance if any of this goes over anyone's head here. It is a bit different, but I hope it's going to be interesting for all of you. And I'm going to talk about functional programming and something called algebraic infrastructure, which is something that's kind of similar, and it does apply to the infrastructure that we run software on, including data science, and how we deploy things, and how we actually make our software, do real useful things in the wild. So my name is Nick Pollard. I'm an engineer at NStack. Please, if any of this interests you, contact me afterwards. So functional programming, who here is aware of functional programming or has heard of it or tried it or is interested in it? Good, that's actually quite a lot of you. Functional programming often can look quite intimidating, as this scroll of maths here might suggest. Some of you might find that actually less intimidating than I do, I don't know. If anyone's interested, a zygohistomorphic preprimorphism is my favorite kind of preprimorphism. That said, it really isn't actually all that scary. Lots of people have defined different things for what functional programming is. If you ask me, functional programming is the art of dividing software into small parts that we know are correct, and then reassembling these parts into a greater whole in a way that preserves that correctness. So the actual steps that we take ensure that we're going to get something at the end that's still correct. And this is a really powerful way to build software. And if you ask any functional programmer, they'll agree, and they'll probably spend 3 hours telling you exactly why it's so great. So in a bit more detail, it's a mathematical approach to software development. I suspect many of you here have a maths background, at least partly. And what it allows us to do is use maths, use the language of maths, the more specific, concrete things, to describe what we're doing, and in particular, to assert very clearly, very mathematically specific properties about the code that we're writing and the software that we're building. And this is really useful because it gives us encapsulation. Now, anyone who's a software developer has come across the idea of encapsulation. But what's really good in functional programming is that having these properties that we know about the code we've written allows us to reason about them. In a sort of traditional object-oriented type encapsulation, it's often all about hiding this internal state. Don't expose this to your users. Don't share it. But if you still don't know about it, if you're still worried that that's going to affect you, if there's some mutable state in there's some things going on you don't know, you don't really have any guarantees of what that code's going to do. And it's kind of this black box that you're trying to use without really understanding it. And with functional programming, you might still not understand exactly what's going on, but you have these properties, these things that will be upheld by that code no matter what. And so you can reason about the way that you connect these, that they are still going to hold certain properties in certain ways if you put them together correctly. And one of the really useful things about maths, using this, this mathematical language that goes back millennia, it's what I call scale agnostic. Mathematicians, they target problems small, large, humongous, any scale, and the same things are still important. So this is a technique that really could be applied to any problem. Now, what kind of mathematical properties might we want to actually declare about our code and assert, and how can we do this? Well, one of the big things in a lot of functional programming is using static typing. So this is, defining types for inputs and outputs of our functions, the kinds of variables that we're going to get in, the kind of values that we're going to return. And actually, in a powerful type system, these tell us an awful lot about the pre and post conditions of our functions. So we can say, again, guaranteed, the value you get back, no matter what this function does, no matter what inputs you put in, what you get back is going to satisfy certain constraints. This allows you to very easily compose functions together, building blocks of code. These might be data science models, these might be things that you've trained, these might be just bog standard code that you've written for menial tasks. Doesn't matter what it is, you have this safety that if you combine functions with the correct types, that's going to work, right? You're taking these things that you know are correct, putting them together, and you still know that what you've created is also correct for the properties that you've stated. So another property that's very useful is something called referential transparency. And this is the idea that an expression is always equivalent to the result of that expression. So particularly in programming, it means that if we apply a function f to some value a, that's always going to be equal to any other time that we apply the function f to that same value a. There's no chance of it changing because of user input. There's no chance of it changing because of randomization. We are asserting that this function is going to behave in this controlled manner. And many functional programming languages allow us to assert this property. And when we know that, not only do we as programmers know that, but our compilers know that. And they can rewrite the code that we're doing based on that property. So for example, if we call that function twice with the same value, the compiler can just call it once, cache that value, and reuse that value. Because we know mathematically that is a mathematical identity, right? We can change that and it's got the exact same meaning. Now, if you didn't have that property, in certain other languages, you can't assert that. You don't know that that function will actually return the same value when you call it again, because it might have updated some internal state. It might be reading from a database, going to disk, going over the network, and you don't know. So I'm going to talk very briefly about Haskell, which is my kind of computer science poison of choice. This is, depending on your point of view, either one of the most famous functional languages or the most infamous, or possibly both. And one of the most important things about Haskell is that it's pure. So talking about the referential transparency, Haskell functions are pure, so they always return the same thing for the same inputs, but at the same time, they also don't change anything else. A Haskell function, if it returns a value of integer or text, is not at the same time going to wipe your hard disk or delete your database or email something to the Russians. It's safe. The type signature, again, the static type signatures tell us everything it's going to do, and we can rely on that. And again, particularly in Haskell, the type system is very expressive. A lot of people, when they look at static type systems, they think they might be very kind of restraining. They're going to hold them back because they're used to older languages with much more minimal type systems that just couldn't express the same things that Haskell can. So here's a very brief look at some Haskell in the wild. This is a very trivial function, but we'll hopefully explore a little bit of what's going on here. The key takeaway is that in many ways, it looks very mathematical. Again, we're defining functions, so we're not telling the computer what to do. We're not giving a list of imperative steps. We're defining some relations. So here we're saying that the prime numbers are every number from 2 onwards, filtered such that that number is not divisible by any of the previous ones. This is a really succinct, clear explanation of what that property is, without talking through, again, the actual steps that the machine is going to be executing when it calculates that for you. So why are all these things useful? We've got all these great properties, that's great. What can we do with them? So a common thing that we might be concerned with is parallelization. Again, talking about some of the talks here, the data sets that people work with, they're pretty huge. You can't do this one at a time. You can't do it in serial. You can't do it on a single core. You need to distribute. Now, if we want to do that, how do we know that code that we might have written for a single core, a single thread, is going to work in a parallel distributed way? Well, one very common for some very kind of simple tasks, but widely used, is a MapReduce. MapReduce, probably you're all familiar with, but if you're not, very simply, you're going to map each input in some collection to calculate something, and then you're going to collate the results in some other way. In Haskell, with its powerful type system, we would define these through these 2 functions, map and some kind of fold. This is a fold L, which is very similar to reduce, but it's a slightly different sort of encoding of that. And really all this says, again, is that these type variables A, we're going to get something of A, we're going to calculate something of B, which is our result. If you give us a list of A's, we'll produce the list of B, so that's all of our individual results. And then we want to collapse those. And this is this fold L, which again, that might look a slightly intimidating signature of what's going on. But really, all it is here is that we're going to have this B here is actually an initial value. We've got some kind of accumulator that if we give it our sort of initial accumulating value, a new value to be processed, it will update the accumulator. And if we keep running that over our list, we'll get a result. So again, we're clearly stating here exactly what's going on and making sure that we haven't missed anything. Now, with that kind of thing, how do we know that we can safely distribute that. If we want to run that in parallel, concurrently it's out of order. Well, one very important thing is the principle of associativity. Very quick math lesson, you probably all know this, but associativity being able to just reorder the way that we calculate a series of operations. If we're adding three numbers together, it doesn't matter which way round we add them, we get the same result. If we multiply them, again, we can put the brackets anywhere, the result will be the same. And in fact, we can state this for any operation. If we have an operator op, if that's associative, then that law still holds. We can do that reordering. So this is a mathematical property that we would like to state. This is embodied very briefly in the algebraic structure of a monoid. That gives us basically for some set of values, which again in a computer science functional programming way we would say is a type. For any type, it gives us an identity value, a default, a 0, and it gives us this operator that we know is associative. And this is great because, again, when we're distributing, and these operations might get run out of order, it doesn't matter, right? If we know mathematically it's associative, it doesn't matter if we do A plus B and then add C. We can do it the other way around. And mathematically, that has to hold that the result is the same. So in Haskell, we can have a function like this. Fold map, this is actually a slightly simplified version. But the principle here is that if we actually say that this type is a monoid, so this thing here before the equals, we're basically saying this type M has to have this property of being a monoid. If that holds, and again, the compiler here is then going to check that for us. If we can prove it's a monoid, this operation, we can just take our list, apply our operation, and we can safely collate all of them. Now, because this property is enforced by that function, we can write a distributed version of that. A library writer, an engineer can go and do that once. And any time that you need to calculate something in parallel and collate the results in parallel, this is safe to do. You don't need to worry about that. And this is one of the really powerful things of the abstractions enabled by functional programming is to do this kind of thing once and reuse it. So that was a very whirlwind tour of functional programming. I would like to talk now very briefly about something else that I think follows on slightly from that. So earlier I said that I think mathematics is scale agnostic, that it's this general tool that applies to things at any scale. If that's so, can we use this to tackle distributed systems and our infrastructure? So today, when we build software, it's normally distributed by default. Anything really that's sort of interesting in the world going on right now in software is going to be distributed. It's going to be in the cloud. Probably for all of you, if you're building software, you're using cloud machines, you're using cloud software, you're deploying distributed over different machines, different data centers. Everything that you build is communicating. It's using so many different services and processes. It's no longer a single thing. It just is always distributed. This is great. It gives us power, but the downside is it's a lot harder to work with. Deployment of these kind of things can be slow and error prone, and this makes it really, really difficult to work with these kind of things. And what we've seen certainly in our work is that for many people, and particularly for data scientists, it can be easy to build something at a prototype stage, to iterate locally, to build a small system internally that works. But when you want to deploy this in a distributed manner, suddenly you've got to work with all these problems, and it just becomes much, much more difficult to actually do that. And a lot of that, I think, is that because the systems that we're building are really too entangled, the different parts of them are all too connected, too sort of stuck together with each other part. We can't reason about them individually like we like to do with functional programming. So, as I said, in data science particularly, you're working with very large data sets. They have to be distributed. They can't be running on a single machine. They might not even fit in memory. And particularly, again, for a lot of people now, might be working trying to solve these really high-level mathematical problems, and it's really not their job to be writing systems code. It's not their job to be operating servers or anything like that. So right now, probably the main kind of idea people come up with is DevOps. It's a buzzword that's been around for a good many years now. And to me, at least, what that means is bringing the idea of software development practices to operations. Software engineers and computer scientists have built lots of tools for ourselves to help our own work, to automate things. And people are now bringing that automation to deployment and to operations. Well, is this the answer? Does this solve all the problems we have? I would say right now, not entirely. There's still a lot of manual work. Even with the tools that we have now in the last 5 years, we're still in a situation where deployment is really hard. Distributed systems, actually running them and maintaining the infrastructure, still more difficult than we would like. Today, we can get away from some of this, but we're still often dealing with servers and networks, and we're actually worrying about the protocols and the routing and who's talking to who and what order. And the interesting thing there is that when it comes to distributed systems, a lot of this stuff is being connected more manually, specifying what IP is this thing running on, what network, what firewall is that behind, what server has this database on. No programmer today, or at least not a sane one, wires up a function call by hand. Right? If you write code and you import a library, you use a piece of software, and you call out to a function, that's going to be generated for you by a linker or a compiler, or some runtime even. If you're using an interpreted language, maybe you'll run it. The runtime will look up and work out where that function is for you. All you're doing is declaring which thing you want to use. Well, why can't we build distributed systems that way? Where are our distributed systems compilers? Right? This kind of should be a solved problem. So here's another little buzzword I'm going to throw out that I made up earlier today. How about MathOps? The functional programming, what I was saying, the reason that I think that's useful was applying this power of mathematics, this sort of ironclad guarantees, this brilliant abstraction, and that for software development gives us a lot of benefits. These benefits of being able to reason about what our code is doing, about being able to declare exactly what this does in a way that it can be safely used by other programmers and by compilers and automated tools. Could we apply that to operations in the same way? Could we get some of the same benefits? So right now, various people and companies and teams in the infrastructure space are looking at little bits of this problem. Containers are very big right now. Docker, Rocket, things like that. It gives you a rudimentary form of encapsulation. We put things in a container and we limit the way that it can talk to the outside world. Containers normally are immutable. This is another a great part of functional programming. And an immutability of a container is great because we start to creep towards that referential transparency. If I start the same container again later, I'm starting the same code. It's that file system is the same. Hopefully, it's going to do the same thing. A lot of people, particularly at very large scale, are starting to standardize their RPC protocols. So the communication that's a remote procedure call, communication between one part of your software and another part of the system, trying to actually standardize that and enforce what's going on. And really, it's a form of typing, mostly a dynamic point in the sense that it happens when a message is sent, the typing is checked, and that can guarantee that the wrong message doesn't go into a system, but it doesn't tell you that until you've already deployed the system. If you've deployed something and you've connected it to the wrong database or the wrong table or the wrong endpoint, you don't know that until you get a wrong message. In a static language, in programming, we can check that ahead of time, and we can tell you before you even start running anything, sorry, that's not going to work. And the last one is service discovery, which has been big in enterprises for a while, is really growing now, again, amongst a lot of new distributed systems, and that starts to approach this problem of kind of linking. If I want to use a particular service, like a database, a shared concurrent log, or a gateway, I shouldn't have to say exactly which server that's on, exactly which IP or which adapter. What I should be doing really is declaring what I need, declaring some kind of dependency, some named service that I need, and allowing some kind of automated system to hook that up for me. And that's great because that'll obviously bring in, it can bring over failover and load balancing and all those kind of things that are really useful. But also, taking that burden away from me, a maintenance burden of having to tie all these things together by hand. If I'm deploying a bit of code, I shouldn't be a human linker going through and replacing, defining all these config variables before I do it, having to maintain all of these. That should be an automatic part of the release for us. So algebraic infrastructure, as we say it, so we think we can still go a step further than this. If we want to have some kind of compiler for distributed systems, then the compiler needs to know some more about what we've done. So going back to that encapsulation, we want to write encapsulated components that, again, we're being clear and explicit about what they're going to do. We're going to assert some of these similar mathematical properties of, this new unit of deployment. Maybe we're talking about a container now, we're talking about a process or a service, and we want to reason about those in the same way as our individual functions within our functional programming. And if we pull some of the same techniques in, we can start to think about these things in very functional programming terms, but at a larger scale. And particularly in a data science use case, perhaps, we can look at that a trained model is a very simple pure function. It's going to take an input, probably some vector of features, or some other similar pre-processed value, and it's going to output some prediction. It might be a classification or a regression. It could be an unordered set, like someone was saying earlier. It could be a huge number of things, but it's going to give you one result. And your trained model, if it's been trained, if it's not retraining online, it is a pure function. If we give it the same inputs, it's always going to classify it the same way, or it's always going to predict it the same way. And we can treat our data sets as immutable values as well. If we have a new data set, if we want to change some values, we should be considering that a new immutable value. And by doing this, we can then start to reason again that if we predict the same data set, it'll be the same. If we train something on the same data set, it'll be the same. If we want to train it again on a different set of inputs, that's a new data set. So we want to get these sort of same guarantees again. We want purity, which is to say no undeclared state or side effects. If I've got my unit of deployment, if it's going to write to some database, we should know that. That should be a declared part of its interface somehow. Declared to programmers who might use it and declared to an automated compiler. We limit the modes of interaction so that the compiler can reason safely about what it can do with this unit. Can it deploy it in parallel? Does there need to be only one? Can it be moved safely from one server to another? Can it be routed behind a proxy? We can use type safety to enforce that our communications aren't going to fail. Why should my deployed system be running fine and then fail because, well, somebody sent the wrong message to the wrong endpoint and that wasn't handled correctly, and now in the middle of the night my system's gone down. Again, we should be catching that as early as possible, and that should be at build time. If we are declaring, the schema of what type of data we're going to send around and what type our other component's going to receive, then this compiler can check that we're not mismatching there, that we're going to send the right values, we're going to receive the right values, and particularly, if someone has upgraded a component and they've changed the data that's going to come out of there, that we're not going to, silently deploy that upgrade and break the system, because doing that is now a compiler error. Again, this automated piece of software can tell us, sorry, you can't release this new version of your model because the database table that you're going to write into is going to fail if you send it that kind of data. And when we have those kind of guarantees and those kind of safeties, it gives us a real confidence to actually develop and build in a compositional manner. We can build an individual part of the system. And different teams can build these different parts, and they build their small bit, which they write correctly. They guarantee that that small bit is correct. Another team does the same, and when they put them all together, they are going to be combined in a way that preserves that correctness. And we can slowly but surely build a much larger system out of these individual, proven and sort of battle-tested and guaranteed correct parts. And we just know when we deploy that, it's not going to fail, or at least it's not going to fail in the number of ways that we've enumerated. I'm not going to claim that this thing is 100% infallible, and if your data center burns down, sorry, that's not my fault. But we can catch all of these kind of things that are either trivial errors or things that we might not think right now are trivial errors, but in hindsight, 20 years from now, we might look back and say, those were trivial errors. Why did somebody spend 4 hours up in the night fixing that kind of issue? That's trivial. So, to sum up, functional programming, as I kind of whirlwinded through earlier, is a really interesting way of building technology, writing software, and the same techniques we think can be applied at infrastructure. And if we do that, there is a path forward where, deploying infrastructure, deploying distributed systems, and really the general art of writing software. These days, people are not writing a single process on a single machine. If you are building software, you are building distributed software. We should have the tools that doing that is as easy as, building a single local process right now. And obviously, if we can do that, you get all the usual things you'd expect. It's going to be faster, it's going to be safer, it's going to be cheaper. It's just generally going to be, so much better than it will now. And hopefully, if we do that, then we can all build much more better software and do great things. So that is algebraic infrastructure. Thanks for listening. I hope that was at least interesting and not too out there. If you are interested at all in these kind of things, whether it's just functional programming or it's the infrastructure side or anything, the slides are online. I think Eddie said they're going to be probably up on the Applied AI Stuff site later as well. Please go to our website. I'll grab one of the t-shirt wearing geeks over here. And please do contact me as well. I'm always happy to chat to anyone who's interested in this. Thank you.